All right, so here we are, part 8. Now, most of what we've talked about so far are monoprotic acids. There are also molecules known as polyprotic acids. Now, polyprotic acid displayed here would be something like H2SO3. So that can lose a proton and form HSO3 minus, which can lose another proton and form the SO3 2 minus ion. Now, one thing that I want you to know about these is that if you look at those Ka values, the first Ka is fairly low, indicating that it's a weak acid. And then the second Ka is higher, so that's indicating it's a stronger acid. So it holds on to that second proton a little bit more strongly. Now, we write expressions for these, and we write equations or reactions for these. So here, what we're asked for is write the reaction and expression for Ka sub 3 for phosphoric acid. Now for this, it's not really, or it's implied that you need to know that phosphoric acid is H3PO4. That is an acid that you absolutely need to know the formula for. Now, this is a polyprotic acid. Now, just to take a wild guess, how many protons do you think that it has? Well, it's got 3 hydrogens, and all 3 of them are protons. So this is a triprotic acid. Now, y'all as biochemists, chances are you're going to see mostly di and triprotic acids because amino acids, the building blocks for proteins, those are all diprotic acids, and a couple of them have a third proton, meaning that they are triprotic acids. So what H3PO4 can do is it's going to react with plus H2O. I'm going to go ahead and write this out. I'm going to do this for the expressions for all of these reactions. H3O plus H2PO4 minus. H2PO4 minus plus H2O yields H3O plus HPO4 2 minus. HPO4 2 minus plus H2O yields H3O plus and PO4 3 minus. So these are all of the expressions. Now, our Ka3 is going to be for just that third proton. Now, one thing that's important to recognize about this is we care about the concentration of our hydronium ions, which is basically interchangeable with a hydrogen ion, our PO4 3 minus, and last but not least, HPO4 2 minus. Now I omitted one component or one reactant there. Does anyone want to know which reactant? Well, I omitted water. Why? Because that is a liquid. Everything else is aqueous. All right. Now, weak bases. Everything we just did for weak acids has a counterpart for weak base. Key difference, or Kb expression or reaction must include water, because water is going to be acting to give up a proton. So it's acting as an acid, and we're going to make hydroxide. So it's acting as an acid because B is acting as our base. So B ends up as BH+. Now, our Kb expression is the concentration of that BH+, our hydroxide ion concentration, and B. Now, there are some common weak bases that you'll see. Ammonia, NH3, and substituted NH3. So an amine, that's a class of compounds. So ammonia, NH3, and here is our NH3, where we've replaced one of those hydrogens. Rather than NH3, we've put this group right here, the CH3 on it. So we have a molecule that is NH2CH3. Here's the NH2, hydrogen, hydrogen, and then our CH3 right there. Okay, another weak base is conjugate bases of weak acids, our acetate and fluoride ions. Kb expressions are written just like this. And an example, Kb for ammonia, we could go ahead and write that reaction out as NH3 plus H2O yields NH4 plus OH minus. Kb is therefore equal to NH4 plus OH minus divided by NH3, the concentration of NH3. Now an acetate ion. The acetate ion is the ion that forms from acetic acid. So acetate CH3COO minus. There's a couple of ions that you're going to have to get more familiar with and comfortable knowing them. Acetate is a good one. Plus H2O is going to yield CH3COOH plus OH minus. Our Kb expression is going to be CH3COOH times the concentration of OH minus divided by the concentration of CH3COO minus. All right, so knowing those and how to manipulate those are going to be helpful for your homework.